Hey guys, welcome to the third part of this tutorial series where we are talking about React-3 Fiber, React-3-drei and how to get started. In the previous video we talked about meshes and how would you create your own meshes. We progressed up to creating a ball on a floor like you see on the screen, and in this part of this tutorial we're going to look more into depth into cameras and how you can control your cameras to behave in the way you want. I am Sohel and let's get started. So this is the progress we have right now. Our perspective camera we created in the last tutorial is staring blankly into space. And what do I mean by staring blankly into space? If you look carefully at this, you're going to see that the camera is not looking at the sphere. The sphere just happens to be there. It's looking more here because this is the center of the camera, right? Watch as it is looking into space. Let's go to GIMP. Let's go to GIMP and say that this blue colored dot is our target. When you set the positions of the camera, all it does is that, say you set your camera position to somewhere around here. Well, you might assume that the camera would be looking at this, and you might raise the y coordinate of the camera and you would still expect it to be looking at the target. But that's not what happens. What happens is that your camera looks forward, and if you raise it, it will still keep looking forward. So this will start getting out of view. So if you want your camera to be looking where you want, you might want to use something called controls with your camera. There are different kinds of controls. What controls allow you to do is to use your camera in a way that you would want, and like overriding the defaults, right? Because there are lots of defaults that ship directly with Three.js and React-3 Fiber as well. One of the many controls that we're going to use is OrbitControls, and that is what we're going to learn today. You're going to learn how we can now make sure your camera is looking at it, and then we're going to see how OrbitControls help you to stay focused on your target even if you move the camera. Yep, we're going to move our camera today, so you're going to see the scene we have from different angles. So let's jump right into it, and you're going to see what I mean. Let's jump to code. With the perspective camera, let's start writing OrbitControls. It ships out of react-three-drei. So OrbitControls is a helper, just like the perspective camera. No props for now. Let's just render our OrbitControls. Whenever you render this out, it's going to take control over the default camera that you have. And right now, the default camera you have is the perspective camera. So this OrbitControls, wherever you render it, is going to take control of this, the default camera, which in this case is the perspective camera. Go ahead, save, refresh, and now you see that the center of the camera, the center of the scene that you see on your screen is the ball, which means now our camera, although it's above the floor, is still looking at the sphere. But what's more exciting, watch. I drag my mouse, which means I click, hold, and drag my mouse downwards, and you see that our camera is rising, but it is still looking at the sphere. Or you can move your mouse left and right, drag the mouse, and you will see that our camera moves. The ball appears to be not moving stationary, but it is because we're looking at the ball from a different angle. We don't have lighting or any other shadows for now, so the ball would look bland. But that's not the point. The point is we are moving right now. On the x-axis and on the y-axis, we are moving our camera. And that is what OrbitControls allow you to do. The meaning of the word orbit is to just revolve around in a circular path. And that is what we are doing. Watch, when we are here, let's go back to the diagram quickly. This is GIMP, and why am I focusing on GIMP? Yeah, so our camera is now here. Let's imagine that we are going to move our camera left or right, that is along the flow, right? So right now, let's assume we are here and we are looking straight forward to the ball, like so. Now we revolve, and now we've come to the right hand side of the ball, right? And this is where we are currently. right now, looking still at the ball. That's what orbit controls allow you to do. The more you rotate, you're gonna find out that you are actually moving in a circle around the target, because this right here will be a complete circle, right? And interestingly, there is an angle that gets resulted when you join the lines of vision from the camera. This angle is called an azimuthal angle. Remember, the azimuthal angle is how much angle you cover when you move the camera along the x-axis. So, if this is the default position, the azimuthal angle as of now is 0 degrees, and as you increase it, it's going to increase. So now maybe it's 45, now it's 90, and now it's 135, and it continues on before coming to a full 360 degrees, and we end up exactly where we started, the 0, right? And similarly, we have another angle, because you see orbits, we can have two orbits. We can have either left, right, or we can have up, down. And when we measure angles in up or down direction, we use something called a polar angle. Let's look at what the polar angle is now. Imagine now that this, let's choose a color. Let's choose yellow. Let's choose a yellow colored flow right here to represent our flow. Let's say, and our camera is, let's choose another color. Let's choose green. And our camera is, let's say, looking right here at the target, like so. What do you mean by polar angle is if you imagine a vertical line along the y-axis that touches the target and moves up, the angle that this covers with the camera is what you call a polar angle. So if you put your camera down like this, if you decrease the height, what you do is you are actually coming below in a circular path to somewhere around here, and when you are still looking at the target, you're gonna find out that you increased your polar angle. Earlier it was this, now you have increased it to this. So the more you come down, your polar angle increases. The more you go up, your polar angle decreases. So let's say we are here somewhere, we're looking still at the target, we have come in a full circle above, and now the angle you have, this one, it is much smaller. What I mean is that, let's say we have this as our default and we raise it, and we raise our camera. Our current polar angle right now is 0, and right now is 90, and this is maybe, I don't know, 70, 60 something, right? So this is what azimuthal and polar angles mean, and when we work with orbit controls, these are the two angles that we set for revolving our camera, because these are the only two we need, right? When you set your distance with 0, 1 and 5, do remember that when you use orbit controls, it needs to stay in a circular orbit around the target. What do I mean by that is, let's go to GIMP right again, and let's remove all of these. There are too many lines. Let's get rid of this. I think I should just click on new to start with a new canvas. Yeah, so we have a target right here, right? Now if we assume that we have a starting point for our perspective camera, what it does is that the orbit controls also initializes here. So if you say now you want to move on top, let's say you want to move along the y-axis now, having set an initial position, say you want to raise the camera. The way you would do that with a perspective camera is to simply change the position property of the camera, and that would work. Okay, that would work. But the moment you set orbit controls, things get a little tricky, because now there are two components competing for the position of the camera, and both have their own intention. Perspective camera wants to set the X, Y, and Z of the camera, whereas orbit controls wants to set the polar and the azimuthal angle of the camera, and in doing so, changing the position. And they both change the position in a different manner. Why? Let's look at an example. if you want to change, if you want to raise your camera and you increase the Y of the perspective camera, you're going to move along a direction like this, right? But if you do the same with decreasing the polar angle of the orbit controls, you're going to move in a direction like this. Why is it so? Because polar angle works by taking your camera and moving it in a circle, right? You're not moving in a straight line, you're moving it in a curve. So the direction where your camera would move if you were to like decrease your polar angle is different than the direction it would move if you were to increase your y-axis distance, right? So you just have to remember this thing that whenever you're using orbit controls, the trick is to just set an initial position with the perspective camera, and then any change in position that you need to make after you have set it, you're gonna have to make those changes with the azimuthal and the orbit and the polar angles. Do not change this position right here because you're not gonna get an exact position. Say what do you mean by that is, say that you have initialized perspective camera and orbit controls while you are here. Now let's say you go inside and you change the position of this to somewhere along this. You might expect that your camera is currently here looking at the target. But the moment you change the Y, orbit controls will recalculate its own coordinates and shift the camera to where it would have been. So you would expect your camera to be here, but it would actually be here. So that's just something to note. And that's just something to clarify. I mean, when I was first starting with orbit controls and perspective camera, I had a lot of difficulties understanding how it worked because, well, I didn't know much, and sometimes the documentations don't cover these intricate details, so it's very important to know this. Now that we have orbit controls, we're going to take it one step further. Refresh the page, we come here. Now the way that this orbit control works is, well, you click and you drag and you move, right? But what if we don't want our user to drag the mouse in order to move the camera, but if we want the user to simply move the mouse and the camera would move on its own? Let's explore how we can do that. So let's come down here. Let's talk about something. There is a hook that you can use to get access to whatever you're currently seeing on screen on a three.js canvas. We have it on use frame. This is the hook that one of the many hooks that ship directly out of Fiber. Use frame gives you access to whatever frames you are seeing correctly. Use frames and it needs a callback. You see that the autocomplete states that you're going to get two things in this callback. The state is what we need, so we'll only take out the state from this. And we're going to execute some sort of code here, and that's all we need. If you remember, I talked about a render loop in the first or maybe the second part of the video. I think the first part of this series. A render loop, well, if you don't know, is a loop that runs again and again to render new frames. Because each frame is a still image, right? But in order to see a 3D world like this where we're rotating, we're actually seeing 60 different frames per second, right? Because 60 times you're going to have 60 new frames that are placed one after the another that gives you an illusion as if it's moving, but it's actually 60 frames one after the other. And the function that generates this is called a render loop because it runs in a loop and it generates 60 images per second. So it runs 60 times per second. This use frame, whatever function you pass into it in the callback, runs for 60 times a second. Well, that depends on your refresh rate. Sometimes it might run at higher, but your computer decides that, or your device decides that for you. So use frame, just remember, is something that runs whenever you have a frame available. And I think JavaScript developers would know that there is a function called the request animation frame. And all it does is that it checks your system and queries it when a frame is available. What do I mean by frame is available? Well, imagine it in this way. Your system's capability of producing frames, the number of frames produced, is called a refresh rate. Gamers and game developers would know this term. Refresh rate is the number of frames, a maximum number of frames you can create in a second. So if your refresh rate is 60 Hertz, you're going to get no more than 60 frames per second, and that's it. That's the maximum. When you create a loop with, let's say, for I equals 0, let's say you're creating a for loop. Although you can run that loop indefinitely, you don't have any control over how much time it takes for the loop, for one iteration of the loop to get over. And if it happens that you have the loop running at a higher speed than 60 times per second, you're gonna see multiple frames drop off because they never got rendered because your refresh rate isn't high enough. So the way JavaScript manages this is with the help of a function called request animation frame, and whatever callback you pass to the function gets executed only when your system is actually ready to generate another frame. Hence the name of the function, request animation frame. What you pass here is the same function that you would pass here, but this time we're just using react-three-fiber because, well, we can't just do this because we are in React. We can do this with use of it, but let's just use a hook that is readily available to us. And this hook is even more useful because it gives you access to something called the state. Let's see what the state has. If we type state, type a dot, and you're going to see all these different things in the state. Let's explore what it has. It has a camera. Interesting. And this camera is the default camera that is currently set. We have clock, we have controls, we have a whole different thing. Watch, it also has mouse inside it. Let's explore the mouse. Let's console out this piece of property, state.mouse, and see what it has. So this function is going to get executed 60 times per second. So you're going to see this getting logged 60 times per second as we move the mouse. Watch what happens. I refresh here and see this? Okay, so now let's okay, it's way too much. It's way too much. Let's comment this out, save it. But now let's observe what happens. This is a vector 2. Observe. A vector 2 is simply an x and a y. There is no z. So let's pick one at random. Let's pick this one. We have an x, we have an y. So what does this represent? Well, if you remember from the first part of the video, remember how I said that the center of the coordinate system is 0, 0, 0? Well, even in two-dimensional, you have the coordinate system with 0, 0 here. The one difference is that these coordinates are normalized. What do I mean by normalized? Well, we have a coordinate here, and this is, let's say, your device. This is your device's screen, the edge of your device, right? This is the edge. I mean, just ignore the horrible diagram, but yeah, this is your device. Now, the 0 is here. Let's say you have a big enough device such that the point 500 is at the edge of the screen. Well, some user might have a smaller device, let's say a phone, where this might be maybe 150 pixels. If you use the coordinate system based on absolute numbers, this is a problem that will arise because what is 150 for someone here might be 150 for someone here. So how would you solve this problem? Well, we use something called normalized coordinates. Well, in normalized coordinates, no matter how large or small the screen is, you're going to see coordinates ranging only from a -1 to a +1 with 0 at the center. So even on the y-axis, it's 1 here, -1 here with 0 at the center. And this is what normalized coordinates are. It's normalized to the resolution of the device we currently have. So how do we get the normalized coordinates? It's easy. All we need is, just think about it. This is 0, this is 1, this is -1. So this range -1 to 1 actually represents the fraction of the original dimension of your screen. So what I mean by that is that 0.5 would be here regardless for any device, right? So if you have a total width of 300 pixels, what is this distance right here? Well, it's very easy to calculate. All you do is first find out the full width, say 300 pixels. You divide that by 2. That means this is 150 pixels, and then this is 0.5. So you multiply 0.5 with 150. What do you get? a half of 150. I think that's 75. So this distance is now 75, and likewise you can do the same calculation for the y-axis. Keeping that in mind, now this becomes easy to understand what this vector 2 means. This is tracking our mouse position on the screen along this coordinate system, this normalized coordinate system. So if your mouse is here, you would have the x as 1. If the mouse is here, you're going to have the x as -1. Similarly, if you have the mouse here, your y will be 1. If your mouse is here, your y would be -1. So we have access to the mouse. What can we do with the camera? Well, let's see. Now in React, if you know, you can create something called a reference to any component or any value that you want to persist across renders. Let's create let's create an OrbitControls ref. We're going to use a useRef, and we're going to set the default at null. Then we take this, and just like how we do things in React, we're going to set the ref to a ref like so. And all we need now is, let's first see what OrbitControls ref actually has. So we're going to make a use effect, and we're going to only run this once when the current changes, and we want whenever there is something in the current. Otherwise we're going to get a null error. To console out current, so we're going to get an instance of the OrbitControls that we currently have on our scene. Save it, refresh. We have the OrbitControls right here, if you see this on the right hand side. So there's so much inside OrbitControls, so much. And let's just go over each of these to just explain you the terms. You already know what azimuthal angle is. Well, what's a max azimuthal angle? Well, the maximum azimuthal angle that you can have. It is set to infinity. That means you're going to revolve as much as you want, because it's infinity. There is no limit, right? That's azimuthal. Same with polar. So you know these two. Let's quickly go over the other. Where it says, well, auto rotate, you can set this to be true, and then your camera would rotate in a circular orbit on its own. Let's talk about important ones, the enable damping. If you move the camera, you see that it doesn't stop when you stop dragging it. It eases out of its motion. What I mean is that it dampens along the way, right? It smoothly stops. It doesn't stop arbitrarily, like all of a sudden. That is what is meant by enable damping. It's set to true by default. If you use 3Js, it would be set to false by default. But react-three-fiber or react-three-drei makes it true by default. And I think damping looks a bit better than if it just stopped all of a sudden, right? So you have damping. What do you mean by pan is that you can actually move the camera to the left or the right. So press shift and drag the mouse, and you see that you can actually walk around like you want. Like you are now actually, what you are changing right now is the position right here. So you are not changing the angle anymore. You are changing the position of the OrbitControls right now. And when you change the position of the OrbitControls, since this is controlling the perspective camera, so this itself gets changed. So remember, when you use the controls, as I said again, do not manipulate any property inside perspective camera, manipulate stuff inside the OrbitControls, and this in turn is going to control this one. So it makes it easy for you. So we have it. And now we have broken this. I mean, we didn't broke this. Now we are looking at a completely different target because we panned across. This motion is called a panning motion. Let's enable rotate. Well, if you set this to false, even if you do drag, it won't rotate. And enable zoom. Well, if you use the mouse wheel to look in or out, I mean scroll in, scroll out, you're going to see this zoom in motion like you see in any video game. You might have seen this. Getting the angle, getting the distance. The zoom level. Well, this is the zoom level I'm talking about. Here we have a higher zoom, here we have a lower zoom. And that's, I think, all the properties, the important ones you need. And there are getters and setters for, very important, there are getters and setters for azimuthal angle. The setters, and there will be getters. Here's the get, Here's again. So we can get and set the angle, and this would rotate, right? So let's try it out. Let's try it out with so we have the orbit controls reference, right? All we need is to call the function and it would give that to us, right? So let's think about it. Let's forget about the y-axis for now. We only want to rotate along the azimuthal line, right? So how do we do that? Well, let's destructure state.mouse. So we're gonna get an x and we're gonna get a y, right? So we have that now. We're gonna focus on the x first. Let's remove this line. And as we move along the x, now the x value would change. If we have the x value, we can figure out the angle that must be set around the azimuthal line. What do I mean by that is, my nose is blocked, very sorry. All right, so we can do something like, let's safeguard our code. I'm lazy, I'm just gonna copy. And now let's continue inside this. So we are assured that whatever code we write here would only run when we do have a reference to the orbit controls. And we have the x right now. So all we want is to call the set azimuthal angle. Set azimuthal. What am I doing? Set azimuthal angle to B. But before we do that, we need to know the original angle, right? We need to know the original angle, because if we don't know that, we can't set the azimuthal angle, because remember, an angle is the offset that you have from the original position. So we need the original position for now. I mean, let me think for a while. Do we need the original position? We have, I mean, it's just me brainstorming the best way to do this without making this way too complicated. So, let's play around with the values, right? Let's play around. We have x, right? What if we do something like, well, angle to radians? Remember the function we had to convert angle to radians? We say, well, let's set this to be x. So now we're treating x to be a radian value, and since x ranges from -1 to 1, our angle might range from, well, am I doing the math correctly? Okay, let's save this and find out what happens. I'm curious to know. And I move the mouse and nothing happens. This is embarrassing. Let's look why it, oh, and that is because we missed something very important. We changed the controls, we changed the parameters, but we didn't update the camera. The camera needs to be told in a render loop when it is manually changed, right? That's one of the things you gotta remember, is that if you manually change something, you gotta inform the camera that you changed something. And the way you do that, I think there's an update function inside the orbit controls. Let's explore. I can't remember all of these stuff. All I do is log out the object and see. So this update function is, I think, what you would call, let's explore. So orbit controls are current, and if we update this one, it might work. Let's try. Save. And would you look at that, we are revolving, but very slow. There's a very small movement, and that is because radians -1 to 1 is too small for it to make any noticeable difference. So we're gonna set this to something else other than the x. So let's say that the maximum we want our azimuthal angle to be is 30 degrees. So what can we do? let's think for a while. We have the x. Well, let's multiply the x by a factor of maybe 5 for now. Let's save this. Watch what happens. Okay, now we have a greater movement. Let's set this to maybe 20. And now we have a lot of rotation, and I'm not dragging the mouse anymore, right? All I'm doing is moving the mouse right now. I'm not dragging. So this does work like we would expect it to. Maybe 24 would be good enough. Refresh. Yeah, but notice we're moving the mouse to our right, but it's moving. I mean, we're looking at the left. I think gamers would know this to be something called inverted controls. When our expectation with our mouse would be that if we took the mouse to the right hand side, we should see stuff that is on the right hand side of our current target, and our current target is a sphere. So if we move the mouse to the right hand side, which we should be seeing this side, but we are seeing the opposite of that. The way you could fix that is, well, let's just say simple minus here. Now we have reversed the angle. Save. And now this works as intended. Okay, that's good. We're getting somewhere. And now, so now let's, if someone moves the mouse all the way to the left hand corner of the screen, you're going to see that there is a maximum that we can cover, and we can't go further than this, right? I mean, earlier what we had is that we could revolve the full of the orbit, right? But now we have set a limit, and the limit arises because the maximum value of x is 1, and so the maximum value of this is 24. That means you can only move around a maximum of 24 radians. 24 radians is quite a huge value. So why can't we move all the way across? Let's log out, and this is me just exploring. I mean, I'm like that. Let's explore a bit. Let's explore this value right here to see the amount of degrees in rotation. This is 0. This moves all the way, and this moves all the way to the positive. This is weird because this the angle 2 radians. I'm gonna take a pause. Let me explain this even better. This is what I do, you know what, I get lost sometimes in code, and I like to explain things. So let's take a pause here. Alright, so what I did was one of the dumbest mistakes I could have done, right? Angles, well, if you keep rotating an angle, it's not going to spin indefinitely. After every 360 degrees, you're going to end up exactly where you are. So x into 24 doesn't even matter. The moment you have a 2 pi radians, you're going to end up where you were. And so that's why we don't get the full range of rotation. I'm an idiot. We're going to have to restructure this. So what we are going to do is, instead of writing it out like x into 24, remember that the x value ranges from a -1 to 1, right? All we need to do is delete it like so. We have minus x multiplied by the radian of, let's say that since this x ranges from -1 to 1, whatever radians we get out of this value will make sure that it interpolates between that range. So for example, if we want our angles, maximum and minimum azimuthal angle, to be 30 degrees, which means 30 degrees either to the left or 30 degrees either to the right hand side, all we need to do is set this to be a 30, because then the radian you would get out of this would be set into a range interpolated by a value which is either bigger than -1 and smaller than 1. So you're going to get smooth values all the way from -30 degrees to a positive 30 degrees. And to test out our theory, let's make this 90 degrees. So it's going to span that entire 90-degree motion. And this negative sign, well, it's here because Well, because we want to reverse our controls. Like, let's remove these two lines for now. We just want to watch the log, right? Save. What's the log? I come here and I get somewhere around minus 1.56 radians, and that is 90 degrees. And it should be negative 1. Yeah, and it's, yeah, we set the directions properly. Now, let's have this. Copy this from here. Make the small change here. Save. Now watch. We're here, we move, and we have a complete 90 degrees as we approach the edge of the screen. Well, this is what we wanted. We move the opposite way and the opposite happens like we wanted. Awesome. Let's reduce, let's take away this log, and let's reduce the maximum angle to be, I don't know, 45. Does 45 look good? You can play around with the values. I'm just going to set it to 45. Yeah, that looks good. Now let's set it for the polar angle. Right now we don't have a polar angle. But remember, azimuthal angle was something you start counting from the origin. I mean, the line you were currently looking at. Polar angle starts from the top. Remember, polar angle starts from, do we have the diagram? Nah, we don't have the diagram. But polar angle starts from the top, in this case, the top of the sphere. So what I mean by that is, alright, so we have the x. Now let's set the polar angle. But before that, let's log out our result to see if we get the correct one this time. Let's first go. So we have the y, which also ranges from a positive 1 to a negative 1. We multiply the y like we did last time, but instead of just setting any angle we want with angle in radians, remember that our angle has to be offset from 90 degrees. And what I mean is, say we want our polar angle to be 60 degrees. What I mean by 60 degrees is that from the top, it's going to be 60 degrees. So from the ground, it's going to be 30 degrees, right? Because 60 and 30, if you add them, it makes a full 90 degrees. If it's 60 degrees from the top, it's 30 degrees from the ground. So just remember this formula. Like if you want to measure your angle from the ground, you're going to have to do this with 90 minus the angle from ground. Or if you want to measure your angle from the exact point where polar angle does this, you don't have to do this. You just type in your angle. I'm going to use the angle from the ground because it makes it easy for me to visualize it. I'm going to set this to 30, so it's 30 degrees above the ground. And I'm going to cover this with angle to radians function, just like we did it the last time, right? So let's log out this value. And let's see, refresh, we go above, and that is 1.029, and I think that's the radian for 60. Am I correct? Well, we'll know if we set it. So let's set this to be OrbitControls .current set polar angle to be this. Update. Come here, refresh, and yeah, looks fine, but there is one bit of a problem. You see, the mouse is at the center of the screen right now, right? So and the polar angle we have is 0. That makes sense, because since we are at the center of the screen, y is 0. If y is 0, this is 0, and if this is 0, the polar angle is 0, and that means you are staring head on from the top of the screen. Now you might not want that. You might want to start at here. You might, right? So let's think of a way we can solve this issue. Well, we can do that. Let me think again for a while. I'm just brainstorming ideas at this moment. But what if we don't start at y? What if we start at a y minus 1? So the center of the screen is no longer 0, but it's minus 1. Or let's start at 0.5. So the center of the screen is translated to a y of 0.5. that makes sense. Refresh, and still doesn't, because the center of the screen. No, wait, we gotta, can we, I'm just fumbling around. Yeah, it's, we're adding, we're not subtracting, we're adding, right? If we add to y, what happens is that 0 becomes a 0.5. So the center of the screen is no longer 0, it's 0.5. So it's 0.5 angle radians from the top, and so we have an angle. But we can do something else now, and this will require some fumbling around. You're gonna see very soon what I mean. Orbit controls allow you to set a maximum, minimum, azimuthal, and polar angles. So if we set this to be a min polar angle, you can set the minimum polar angles that your camera should be all the time. And let's say the minimum I want is it to be 40 degrees. Let's set it to be 40 degrees. The angle to radians, 40 degrees. And this is the minimum. And what do I mean by minimum is that from the top, it has to be a minimum of 40 degrees. That is, it cannot go any smaller than that, meaning we can't rise above 40 degrees, right? Save, refresh, and now see that this is the maximum we can go. I mean, see, I'm moving the mouse downwards, but I can't rise above 40 degrees, but I can go below it. See this? This is what we want, but let's make a few modifications. Let's make the minimum polar angle to be more closer to the ground, 60, and the max that we can go, because if we go all the way to 90 degrees, we'll see the floor in a thin line, right? We don't want that. So let's make the maximum to be at 80 degrees. That's, for me, it's a lot of maths involved, and what can we do? It's 3D. There's gonna be so much stuff. But yeah, now the maximum, it's 80 degrees, and I can't go below that. See this? I'm locked at 80 degrees. I'm raising my mouse here, but it makes no difference because I am at, so the value is now locked from a minimum of 40 to a maximum of 80. It's locked right now. It's locked. So let's make a few modifications so that when we are at the center of the screen, we should be looking at the default. This requires you to just, really play along the values. Let's make it 7.5. Refresh. Let's increase it even more with maybe a 1. Let's see if that helps. Yeah, I think this does just fine. Yeah, this looks great. For now, yeah, this looks great, and I think we can, yeah, so that's it guys for this tutorial. What we achieved was that we controlled our perspective camera with Orbit controls. We played around a lot. Well, I played around a lot because I have trouble remembering so many properties. What I do is log them out and find the correct ones, and that is also because there are several differences between how you do things with 3Ds versus how you do things with react-three-fiber. And that is what I want you to take away from this tutorial. What is more important than remembering is knowing a way to find out even if you don't remember. And the way you do that with three-fiber is you log out entire objects, and then you look at the objects, their properties, and then you try to understand what they do. So that's it for this tutorial. Stay tuned for the next in series. Next tutorial, I think it will be about lights and shadows. We're gonna make the scene look much more realistic, but for now we're stuck with the camera, and that's okay. Make your progress, and I'm gonna see you in the next video. Like this video, but most importantly, leave comments if you wanna drop any criticisms or you wanna ask anything. I'm also active on Twitter. Follow me over there at RealCaptainWolf. Yeah, that's my username, and I'll see you guys in the next video.